Rank better results with gradient-boosted trees in Python. You will build a tiny ranking pipeline, train a gradient-boosted regressor to order results, and measure quality with NDCG and pairwise checks. By the end, you will see top 3 items per query and understand how tree count and simple features change ranking behavior. I'm Professor Pi, teaching search and IR from basics to advanced in simple Python. Learning to rank matters because it directly optimizes ordering where position is everything. We care about NDCG, which measures ranking quality with position-aware relevance, so that higher relevant items at the top score more. The trade-off is latency and model size when you add more trees or deeper trees. In practice, you might improve NDCG by a clear margin at the cost of slightly longer scoring time per item on 100,000 item catalogs. The intuition is simple. Instead of scoring documents by raw similarity alone, we teach a model to predict a score that leads to better orderings. This shines when you have labeled relevance or clicks and multiple features per document. It can struggle when labels are noisy or when latency must be sub-millisecond because complex ensembles cost time. We will work on a small product ranking example throughout to keep things concrete. We will build a tiny product dataset, test ordering, train a gradient-boosted regressor, track NDCG as we add trees, and finally pick the best model to output top 3 per query. Now we create the toy dataset and a baseline scoring rule. This snippet builds a tiny ranking toy set and applies a simple score. It creates a few queries and a small catalog of product items with relevance labels that mimic clicks. The code also computes a baseline score using a simple feature or heuristic, like text match strength or a similarity estimate. That baseline gives us something to beat and helps show what the model learns. You will see feature vectors for each item and how the simple score orders them. If you change the baseline weight, the ordering shifts and the model will start from a different error pattern during training. Next, we measure pairwise ordering for a sample query. This snippet measures pairwise ordering correctness for one query. It compares every pair of items in the query and checks if the higher labeled item also has a higher score. That gives pairwise accuracy, which checks whether item pairs are ordered correctly rather than looking only at top positions. Pairwise checks are intuitive and fast for small sets and help diagnose whether errors are global or just at the top. If you increase the number of pairs by adding items, the metric becomes more stable, but also slower to compute. This single query view helps us target model fixes. Next, we train the gradient-boosted regressor and score a query. This snippet trains a gradient-boosted regressor and ranks a query. The regressor is an ensemble that adds small decision trees sequentially to reduce prediction error. We fit the model on features and relevance labels from the toy set, and then use the model to predict scores for items in a held-out query. The snippet shows how more trees and deeper trees change predictions. Increasing tree count typically reduces bias and can improve ranking, but too many trees or high depth risks overfitting on small data and raises scoring latency at deployment. Next, we compute NDCG and compare performance across tree counts. This snippet computes NDCG and shows improvement from more trees. NDCG, which measures ranking quality taking into account position and graded relevance, is computed for each query and averaged. The code evaluates the baseline and the model with different tree counts to show learning progress. You will see NDCG rise as the model captures better ordering, and the snippet highlights diminishing returns beyond a certain number of trees. If you change the evaluation cutoff, like top 3 versus top 10, the observed gains can shift because the model may help top positions more than lower ones. Finally, we select the best model and produce results. This snippet selects the better model and outputs top 3 per query. It compares NDCG or pairwise accuracy between candidate models and picks the one with the best validation metric. The chosen model is then applied to each query to sort items and print the top 3. This mimics a small production step where you pick a single model and serve its ranked list. If you prefer lower latency, you could choose a smaller tree count, even if validation NDCG is slightly lower, trading a little quality for faster scoring. Recap: learning to rank with gradient-boosted trees means training a score predictor to produce better orders. Use it when you have relevance labels and care about top positions measured by NDCG. One caveat is the latency and overfitting risk as trees grow. Next step: scale this exact pipeline by evaluating on a larger corpus and adding an approximate nearest neighbor pre-filter, so you only score a small candidate set per query. If practical IR and hands-on Python help you, subscribe and watch the rest of the series.